Hello everyone, we are Group 4. Our topic is about photoluminescence spectroscopy, and our group members have Wang Jianying, Li Wenxun, Hu Jiaduan, Zhang Mengrui, Chen Kejun, Lin Mengchen. These are our contents. We will first talk about the fundamental working principles of photoluminescence spectroscopy, its procedure and instrument, and introduce its spectrum analysis. According to the introduction, we will look deeper into some real cases to let everyone have a better understanding of PL. Next, we will discuss about affecting factors and some comparisons of PL. Then finally, do a quick conclusion for everyone. The first part is about a principle. In this section, I will introduce the fundamental principles of photoluminescence spectroscopy, or so-called PL. I will explain how PL occurs, what electronic processes take place inside a material, and why PL can be used to probe band structures and defects in semiconductors. So, what is PL? PL is essentially an absorb, excite, emitted processes. A material absorbs a photon, an electron is excited, and when the electron recombines with a hole, light is emitted. The emitted photon carries information about the material's band structure and defect states. And according to delay time to emit light, there are two kinds. One is fluorescence, and the other is phosphorescence. Fluorescence is a fast emission that occurs when an excited electron quickly returns from a singlet state to the ground state. And phosphorescence is a delayed emission that occurs when an excited electron slowly returns from a triplet state to the ground state due to spin-forbidden transitions. And our report is mainly focused on fluorescence. As mentioned before, the PL processes consist of three steps: excitation by light, relaxation of the excited carriers, and finally radiative recombination that produce detectable PL photons. The first introduction is about excitation. After photon absorption, electrons are promoted to conduction band and leave cells in valence band to create electron hole pairs. This electron hole pair provides the energy for PL emission, as all subsequent radiative processes originated from their recombination. And second process is relaxation. Although the electron is initially excited to a high-energy state, it quickly relaxes to the bottom of the conduction band or forms so-called excitons through photon scattering in around picosecond. An exciton is a bound electron hole pair, similar to a hydrogen-like system. Exciton emission appears slightly below the band gap and is typically sharp, making it an important indicator of optical quality. Because of relaxation, PL emission therefore occurs from the lowest available energy state, not from the initial excitation energy, and that's why the energy of PL light is always lower than the energy of excitation light. Just like relaxation process in PL, electrons and holes do not always recombine radiatively. They can undergo non-radiative recombination via SRH defect, Auger processes, or surface recombination. These pathways reduce PL intensity, so PL is also a sensitive indicator of material quality. SRH, or so-called Shockley Reed hole recombination, is a non-radiative process in which carriers are first trapped by defect state and then recombine with opposite carriers through these traps. Auger recombination is where the energy released by the recombination of two carriers is transferred to a third carrier, exciting it instead of emitting light. The third one is surface recombination. It is also a non-radiative process in which carriers recombine rapidly at the material surface due to high density of surface defects. The final part is about emission. The core of PL is radiative recombination between electrons and holes to finally generate PL. There are three major types: band-to-band, exciton, and defect-related emission. Each produces characteristic PL peaks. Band-to-band emission in PL is a radiative process where an electron directly recombines from the conduction band to the valence band, emitting a photon. It dominates in high-quality samples with few defects and presents narrow and high-intensity PL peaks with energy close to band gap energy. And second, exciton emission is a radiative process where a bound electron-hole pair recombines and emits a photon. It is usually seen in wide bandgap materials with much narrow PL peaks, and with energy slightly smaller than bandgap energy. Finally, the defect emission is by carriers recombining through defect state and emit photons. It will be observed mainly in material full of defect or wide bandgap oxide. Its PL peaks is broader and with energy much smaller than bandgap energy, usually around visible light range.
Now I'm going to introduce the PL procedure and extraction and Li And the first part I want to talk about the instrument, and the below figure is just show the simple scanning of fluorimeter or spectrophotometer. And a fluorimeter or spectrophotometer use a double beam system to correct for source fluctuation. The sample being passed through an excitation filter, excites the sample, and the emit fluorescence go through an emission filter before reaching the detector. The reference beam is attenuated and also sent to a detector. The electronics and computer calculate the ratio of fluorescence to reference intensity, canceling source variations. And the next part is just talk about a light source since the luminance output signal magnitude and sensitivity are directly proportional to the source radiant power. Hence, high power source are used. And first, we can use mercury vapor lamp. And the second is summer lamp. And the third is light emitting diodes or core LED. And finally is lasers. And this part is shows the instrument for design about fluorimeter and spectrophotometer. And for fluorimeter, a typical filter fluorimeter use a mercury lamp and two photomultiplexer tubes. The source beam is built into a reference and a sample beam. The reference beam is attenuated and sent to one detector, while the sample beam excites the sample pass through a second filter and reaches the other detector, the system calculates the ratio of sample to reference intensity allowing simple and local quantitative fluorescence measurement. And for spectrophotometers, the spectrophotometer with two grating monochrometers can measure both excitation and emission spectra, semi-length radiation passes through the excitation monochrometer with part going to a reference detector and part exciting the sample. The emit fluorescence is dispersed by the emission monochrometer and detected. Since the intensity depends on the lamp detectors and monochrometers, these spectra are not suitable for quantitative analysis. And this part is just talk about a spectrophotometer with an error detector, and the figure just below it shows how it works about an error detector and a spectrophotometer with 3D. And for this part is just the error detector spectrophotometer excitation being get through sample field that disperses along the X-ray plane by emission polochrometer. The 2D charge transfer device we call the CCD disperses the excitation radiation in the X-ray plane and disperses the emission monochrometer radiation in a YD plane. So an error detector spectrophotometer can provide a 3D total lumen sense spectra with complete excitation and emission spectra of a compound. Total spectra can be obtained exceptionally fast, which is smaller than 1 second, and also it can be used to analyze mixture of fluorescent species. And now I just talk about experimental procedure since there are so many PLO extractments, so I take TRPLO as example. The first step is that we can use excitation and triggering a pulse laser picosecond or femtosecond excite the sample at a set recitation rate with a laser or signal generated trigger for timing. The second step is that sample collecting optics. The beam is focused until the sample emitted light is filtered and sent to a detector via free space or fiber. Setups can be confocal or wide field with optional spectrometer of environmental control. And the last step is that photon detector emitted photons are collected by time resolved detectors such as PNT, SPAD, or SNSPD. And the last part, we just talk about the specimens, about the PLO. And so first is that phosphorus is more likely when a molecule includes heavier atoms that enhance orbital coupling, since this increases the probability of inter-system crossing between singlet and triplet electronic stacks. And the second is that PLO is useful across many material types such as semiconductors, nanomaterials, organic compounds, and perovskites, or they can also used to dynamics of excitation as well as defect states and Bankcap energy. And the next part is just talk about the spectral analysis and welcome Hujare to explain this part.
My name is Hu Cha Tuan. Now let's move on to section 3, spectrum analysis. When we look at a typical PL spectrum, first we need to understand the axis. The x-axis represents the photon energy or wavelength, while the y-axis shows the relative intensity of the light emitted. From this graph, we can extract three key parameters to evaluate the material quality. First is the peak position, second is the peak intensity, and the final one is the full width at half maximum. I will explain each of them in the following slides. Let's start with the first parameter, peak position. Fundamentally, the emission energy corresponds to the bandgap energy of the material. You can think of this as the material's fingerprint. For example, if we see a peak at roughly 3.4 electron volt, we know the material is like gallium nitride. However, if the peak shifts to a higher or lower energy, it indicates the change in the material's condition, such as doping effect, strength, or change in temperature. The second parameter is peak intensity, which tells us about efficiency. Simply put, intensity is proportional to the quantum yield. A higher intensity usually suggests high crystal quality with few defects, meaning that radiative recombination is dominant. On the other hand, a weak signal implies that energy is being lost to non-radiative centers, such as defects or simply dissipated as heat, so we always look for a stronger signal. The third parameter is full white at home estimate, or line white. This indicates the purity and uniformity of the material. A sharp, narrow peak represents high crystallinity and a highly ordered structure. Conversely, a broad peak suggests energy fluctuation. The burden can be caused by thermal vibrations, a high density of impurities, or size vibrations in the case of nanomaterials. Finally, let's distinguish between the two main types of emission. On the left, we see the near band edge emission. It corresponds to the band gap and is usually sharp. Our goal is to maximize this peak. On the right, the broad lower energy peak is the deep level emission, which comes from defects or traps. To verify if we have a high quality material, we calculate the ratio. A high ratio of MBE to DLE intensity proves that the crystal quality is excellent. That concludes my part on spectrum analysis.
Hi, I'm Ray, and in this section, I will present two real-world applications of photoluminescence, LED lighting and bioimage technology. Our first case is white light LED, and in fact, there is no semiconductor chip that can directly emit white light. To create a white light, we rely on a method called phosphor conversion. As you can see on the top of the right picture, the core of LED is a semiconductor chip, typically made of indium gallium nitride. This chip will emit blue light, not the white light. To create the white light, researchers coat the blue chip with a yellow phosphor powder, which shown in the bottom of the right picture. And this is where the photoluminescence occurs. The yellow phosphor absorbs the energy from the blue light and converts it into the yellow light. When the emitted yellow light mixes with the remaining blue light, our eye will perceive the combination as a white light. This is the standard mechanism behind white LED. And we can talk about the next application, bioimaging and labeling. The main challenge in microscopy is that biological cells are typically transparent or very dark. This makes researchers extremely difficult to distinguish specific virus or protein. A protein. And to overcome this, scientists use fluorescent tagging. We attach phosphor to the target of interest. For example, specific receptor on the surface of cancer cells. This tag acts as a light beacons, allowing us to see what was previously invisible. When we illuminate the sample with the light of specific wavelength, like UV or blue light, the attached dyes will absorb the energy, and they will re-emit the energy as a bright fluorescence such as green or red light. This creates an extremely useful effect because the background tissue doesn't possess these tags. It will remain dark. Only the target areas will glow, and this provides high contrast. This contrast allows researchers to track cells with high accuracy, which is crucial for medical diagnosis. And next, chapter will talk about the affecting factor and comparison. So let's welcome the Chen Kejun.
Okay, next is my turn. My name is Chen Kejun. Based on my partner explanation, I believe everyone know more clear about the fundamental concept of PLO and the basic analytical methods. In my section, I will introduce the affecting factor and the comparison between the PLO and the UVV absorption. And this one is about the affecting factor. I will introduce three parts. It's quantum yield, material property, and the temperature. And first part is about the quantum yield. Quantum yield tells us the efficiency of a light-induced emission process. And this is the equation, and the K is represent the rate constant, and radiative recombination is the photon emitting process we mentioned earlier. And non-radiative recombination, maybe someone is forget, is that including the intersystem crossing, external conversion, and the internal conversion, where the excited state loses energy without emitting photons. And next part is about the QY can do what. And the first one is that it's strongly related to material quality. If the material has a fewer defects and non-radiative recombination decrease, so the QY increase. And second part is that QY also reflects surface quality, especially for the nanomaterials. So where the surface some impurity may can trap the period and reduce emission efficiency, so low QY. And because QY directly indicates how well a material emits light, so it is a very important parameter that to design the emission devices. And there is a question, is that why we need QY? And QY helps us understand why a material does not emit as much light as expected. And a material might absorb light very well but emit poorly either because it is intrinsically not a good emitter, or because non-radiative recombination dominates, so greatly reduce its emission efficiencies. And next part is about the material structure. And I take the gallium nitride for example. We can see that different crystal structure is a clear shift in PLO peak. And this is why. And this is because different structure have different symmetry. And structural distortion causes energy level splitting, just like this one, splitting. So it causes different transition, and different transition lead to the different band gap, and finally the PLO energy will different. And this image is telling that the different structure have different band gap. And next one is about the material size, and size is another important factor. And from the image, we can see that different particle size show different peak position and width. And for larger material, the lattice expansion is made alert the balance band measurement in the energy diagram and change the carrier recombination or generation rates will result the band gap change. And second is that for nanoscale material, quantum confinement will become dominant. So when the size decreases to the quantum ring, the PLO peak shift to the higher energy and the peak become broader. And the next part is about the temperature. And I take the gallium selenium for example, and temperature increase, the intensity decrease, and peak redshift, just like this one, the energy decrease, and the peak broaden. And first one is that temperature increase, the lattice vibration will seriously, so energy is lost by heat instead of light, and so the intensity decrease. And next part is that the lattice expansion strongly, so the band gap becomes smaller, just like previous slide, and so the peak redshift, just energy decrease. And second, and the third part is that photon scattering increase, so energy fluctuate more, and energy spread wider, so the peak broadening. And there is a small conclusion is that non-radiative recombination is too strong, then the QY will decrease, so the intensity will become very small. And another is that higher temperature will lead to the intensity decrease. So it's like the previous slide. And PLO also has some limitation. The first one is that it cannot determine which elements are present, unlike XPS or AES. And another is that it not work for pure metal because they do not have a clear band gap. And there I introduce the comparison. And this time I will compare PLO only with UV-Vis absorption, and from the spectra we can see that PLO and the absorption look complementary, but they reflect different aspects of the material. And first part is about what is measured. UV-Vis absorption is measured light absorbed, and PLO is measured light emit. And in a material type, UV-Vis absorption can measure almost any material, but PLO only can measure the material can emit light. And previous I say that metal cannot be measured by the PLO. How about in the absorption? And the material metal cannot be measured by UV-Vis absorption, but it can be using another technique called atomic absorption. And third part is that band gap determination. And PLO energy is often slightly lower than the true band gap due to the non-radiative losses. And another part is that absorption can determine the band gap more directly. And by converting absorption data into a tau plot, we can obtain a value that is usually closer to the intrinsic band gap.
Okay, let's welcome the Lin Mengchen.
To conclude our presentation today, I would like to summarize why photoluminescence, or PL, is such a critical tool in material science. If there is one core message to take away from our analysis, it is this: PL is a highly sensitive indicator of material quality. Whether we are looking at semiconductors or nanomaterials, the light emitted tells us the story of what it is happening inside the atomic structure. In this final section, we will break down exactly how we interpret that story through the PL spectrum. First, let's briefly recap the fundamental mechanism that generates the data we analyze. We can summarize the PL process in three simple verbs: excite, relax, and emit. First, the excitation. It starts when the material absorbs photons. This energy excites electrons, pushing them from the valence band up to the conduction band, leaving behind holes. This creates electron-hole pairs. Second, relaxation. These carriers don't stay excited forever. They rapidly lose energy, often through heat or interaction with photons, and settle to the edges of their respective bands. Third, emission. Finally, the electrons and holes recombine. When they do, they release their remaining energy as light. However, there is a crucial competition happening here. The energy can be released as light, which is our radiative path, or it can be lost as heat through defects or traps, which is the non-radiative path. This competition is why PL is so useful. If your material has many defects, the non-radiative path wins, and you get very little light. If the material is high quality, the radiative path wins, and the PL signal is strong. When we look at the resulting spectrum, we aren't just looking at a pretty curve. We are analyzing three specific diagnostic metrics: peak position, peak intensity, and full width at half maximum. First, let's look at peak position. The position of peak on the energy scale corresponds to the material's band gap. This acts like a fingerprint. It identifies the material. For example, if we see a peak at specific energies, we know we are looking at gallium nitride or another specific semiconductor. Furthermore, if this peak shifts to the left or right, it tells us that the Material might be under strain, heavily doped, or affected by temperature change. Second is peak intensity. The height of the peak is directly correlated to the Crompton yield. This is our primary measure of quality. A high-intensity peak indicates high crystallinity and excellent material quality. A low-intensity peak serves as a warning. It usually implies a high density of defects, where energy is being lost to those non-radiative passes we discussed earlier. Third is FWHM. This measures the uniformity of the sample. A sharp, narrow peak tells us that the structure is highly ordered and uniform. And a broader peak suggests noise in the system. This could be due to thermal vibration defects or variations in particle size. Finally, it is important to understand the external factors that can alter this matrix. We identify three main factors that change the spectrum: temperature, structure, and noise and size. Temperature has a profound effect. As we increase the temperature, three things happen. The intensity decreases because more energy is lost to heat. The peak redshift, meaning it moves to lower energy because the band gap actually shrinks as the lattice expands. And the final one, the peak broadens due to increases phonon scattering. The next one is structure. The crystal phase matters. Even with same chemical formula, different arrangements like woodsite versus zinc blende have different symmetries. This changes the band gap and consequently shifts the peak position. Next one is the size. This is particularly relevant for narrow materials. Due to quantum confinement, changing the physical size of a particle will shift its energy levels. This allows us to tune the color of the light simply by changing the size of the material. In summary, by analyzing the position, intensity, and width of the PL spectrum, we can determine the identity, efficiency, and structural quality of a material without damaging it. And that's all for our presentation about photoluminescence. Thank you very much for your attention.